Let's look at Euclid's book 3 proposition 10. The proposition says that if we have a circle, another circle cannot cut this circle at more than 2 points. More than 2 points means it can be 1 if it is just touching it, and it will be 2 if it is crossing. If it is not touching, it is actually cutting. Then it will be 2 points. The proposition says it can't be more than 2 points. So let's see. I'm sure instinctively or intuitively you know that we cannot really draw a circle which cuts this circle at more than 2 points. So let's tweak, because we are going to use proof by contradiction. So let's tweak the shape of this. But remember, assumption is that this green figure is a circle. And based on that assumption, we keep going forward till we reach a contradiction. Now, here, these two circles are intersecting each other at 4 points. So let's mark those 4 points. Remember, the only way in which we can prove that this is not possible is by trying to figure out the center for both these two circles. Okay, so we know how to find a circle, right? So let's join B and H. Let's join B and G. Now let's bisect BH. We know how to do that. Intersection points, joining the line, marking the intersection. So K is the midpoint of BH. So now that we have got that, let's hide this. Similarly, we are going to bisect BG. So again, circle, circle, intersect, intersect, line, and intersect. So L is the midpoint of BG. So let's again hide all this. Now let's mark the other points of intersections between this line and these two circles. So E, M, N, O, A, C, I. Just to get rid of these lines, let's join M and E, and let's mark the points of intersection. Left out once. Okay. Now we can hide these two lines. Let's focus on these circles one by one. Let's look at red circle, circle C. Now here, if you notice, AC is bisecting BH or HB. These angles are equal to each other. Since we know there is a proposition which says that a line standing on another line dividing the adjacent angles into two equal angles, then these angles are right angles. Now, based on another proposition, we know that if this is the situation, then the center lies on AC. Now, let's look at this BG. Again, continuing with the red circle, circle C. We have NO bisecting this BG by making adjacent angles equal. And we know that if they are equal, then they are 90 degree or right angles. We know that if this is right angles, then the center lies on this line. We know now that the center of circle C lies on AC and NO. Now the only point at which they are intersecting is this point. That means this is the center of the circle C. Now let's look at the green circle, circle D. We follow the same logic. This line ME is bisecting BG at right angles. So we know that the center of the circle D lies on ME. Similarly, if we look at the line segment HB, di bisects it at right angles. So, which means the center of the circle D lies on DI, and the only point in common to ME and DI is P. So we have reached a conclusion that the center is common to both the circles. Now, if two circles have a common center, we know based on previous propositions that they will not be intersecting each other. So since this is impossible, that means our assumption was wrong that they can intersect at more than 2 points. So that is proposition 10 of Euclid's Elements, book 3. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it. If you feel somebody else will benefit, share it. And most importantly, if you find any mistakes, please don't hesitate to put it in the comments so that I can rectify it. That's it for now.